NOAA's Global Systems Division in Boulder, Colorado creates the systems that help weather forecasters save lives and property. Case in point, the Big Thompson flood of 1976.
The Weather Service had not done very well on the Big Thompson flash flood. They really didn't know it was happening. They said, we need a system that really does this right.
So a team of scientists in Boulder determined to bring better technology into weather forecasting. One of the first key innovations was PROFS, the Program for Regional Observing and Forecasting Services.
Before PROFS, we used to have fax charts, which were models on the wall.
We saw a whole lot of observations around that weren't being used for that purpose, let alone for numerical weather prediction.
Computing technology of old was extremely expensive, and that was a barrier to entry.
The bit rates for data was less than 10,000 bits per second. That's inconceivable today.
The team in Boulder knew they could pull weather forecasts into the future, and in 1980, PROFS was formed.
What we were trying to do in PROFS is really build a modern, display-based system that had motion where the forecaster could see the atmosphere really like it really was and do a much better weather warning and forecast.
We're here in the Environmental Research Lab in Boulder, Colorado, which is part of the National Oceanic and Atmospheric Administration, to talk to you today about a new and exciting program, the PROFS program.
And our job really was to work very closely with National Weather Service because they had decided that their next operational system was going to be sort of built around what we were developing here in Boulder.
That was a key focus, building systems based on need, whether it was the National Weather Service
We were always presenting things to a forecaster.
or an increasingly important client, the Federal Aviation Administration.
In the mid-1980s, forecasting of upper-level winds especially was not very good. It was recommended to have a rapid updating model that would focus on using of automated aircraft observations.
The 1980s was a decade rich with innovations in modeling and observations. New models like LAPS and MAPS improved local and regional weather forecasts.
After our system was made available, they were able to see composited products from all these data sources.
And better observations also made significant contributions, like the wind profiling network which NOAA deployed in the 1980s. In the 90s, those wind profilers saved lives during a tornado outbreak.
And the weather forecast models did not capture very strong winds high in the atmosphere. One of the profilers in Tucumcari, New Mexico did detect these very strong level jets. That led the forecasters to issue a warning many hours ahead of time, and it's been said that almost 600 lives were saved because of that few minutes of warning.
In 1989, led by Sandy McDonald, this team became the Forecast Systems Laboratory.
We also developed our modeling capability, high-resolution models, and high-performance computing capability.
FSL was an early adopter of massively parallel technology.
And the challenge would be, can we make that computer work on our weather and climate applications?
And a lot of the work done on the models and in high-performance computing really started when we started an aviation program improving our high-resolution modeling so that it really met the needs of air traffic decision-making.
In the 1990s, FSL's big innovations included the Ruck model.
In this fast-moving world, we needed faster-moving models that allowed better decision-making. So the rapid update cycle became, in 1994, the first NSET model to run at a frequency less than every 12 hours. For storm forecasting, but also for aviation, also for energy.
Also AWIPS, which changed operations in weather forecast offices.
If you went to a forecast office in the early 90s, you would see a PC here that had satellite data, and then you would see something called the PUP that had all the radar data. And over here you'd see local data sets that they may have. You'd see these tables with printouts of the models. And what AWIPS did is it combined all of those into one screen for the forecaster to look at.
FSL also used new technology to show audiences another way to look at our planet.
And I thought, gee, why don't people display things on spheres? I found a beach ball, I painted it white, went out in my garage, set up a ladder with a video projector, and put it on to the beach ball, and it looked pretty darn nice.
In August of 2001, Dr. McDonald explained to me that he wanted to create a system where he used external projection to animate the Earth or other data sets on a sphere. And he thought this would be very captivating. Turns out he was right. Today there are over 115 Science in a Sphere installations around the world. FSL is now the Global Systems Division, part of NOAA's Earth System Research Laboratory.
Given the successes GSD has had in the past, I'm confident that we're well positioned to bring world-class science and technology into weather service operations.
GSD continues to innovate in high-performance computing.
GPUs, graphics processing units. There's lots, millions of computers that are all packaged together onto boards and chips that then collectively can be used to solve any science problem.
Developing better user interfaces.
With the graphical forecast editor, a user can say, I want to know what the forecast is for my particular point.
And new models that improve forecasts.
We developed the high-resolution rapid refresh, which just went into operations this year.
GSD applications are a crucial part of the forecast and warning generation process. Without them, we couldn't deliver that forecast every day for you. What's the weather going to be? What are my considerations for weather today? And most importantly, those warnings that keep Americans safe whenever severe weather threatens.
We had a case a few years ago where there was an airliner crossing the Atlantic, and he'd encountered unexpectedly strong headwinds. The air traffic controller looked at our model. They discovered that at another level, a little lower down, the headwinds were less. So the aircraft went down to that lower headwind area and went on and landed without incident. Now maybe they'd have landed without incident anyway, but I like to think maybe our stuff saved some lives.